All right, I think I am live, hopefully. As always, let's see here. Looking promising. As always. Whoop. Okay, I can hear myself. Twitch chat, Twitch chat, Twitch chat, Twitch chat. Is anyone here? Maybe. Ooh, how the heck does this thing work? This. All right, there's some number of people here. All right, who has questions about TCP or IP or Ethernet or ARP? But not level specific questions, but concepts in general. Something that's just not making sense, Yeah, be good to go over that. I got a little bit of a working environment set up, hopefully. Hello. Got a little bit of a working environment that I went ahead and set up. I basically modified the challenge code a little bit, started up level 1, said, hey, we're not going to run the challenge, and then added in this code. Pretty easy for me to do it because, I wrote this infrastructure for this series of challenges, so I know how it works. It'd probably be pretty cool to export this challenge as a library. Or like the core infrastructure of this challenge as a library, because it kind of does some stuff that nothing else really does. The ability to spin up these networks as like a Python library, like that just doesn't exist. And it's kind of cool. Like we basically define a network. This network has 2 hosts. We got a shell host. In this case, we got a demo host. And then we start up the network. And we also run all of this in a sandbox for all sorts of reasons. And then this little demo host, starts up, and every 5 seconds it prints hello and I am my name. Okay. Specifically unsure how to go about doing a man-in-the-middle attack. Okay. How to do a man-in-the-middle attack. Well, I think we can learn a whole bunch of concepts by talking about doing a man-in-the-middle attack. That's probably a good place to point in the direction of for this office hours, and we're just going to talk about a whole bunch of things along the way. I'll check in on the chat every once in a while, do my best to do that. I need to get like an iPad or something on the side for a Twitch chat. Future goals. Okay, so I guess also one thing in case it's unclear for people watching, we're on intercepting communication. This tab, don't need this tab, don't need that tab. And it's due in a week. So hopefully everyone is working away. Okay, so let's talk about man-in-the-middle attack. So first, let's just quickly maybe approach this conceptually. What the heck is a man-in-the-middle attack? Okay, so we have some network, call it some network, which has a whole bunch of hosts on it, right? Just a local network. All of these agents on the network in this case are an Ethernet packet away from each other, right? Just one hop, or I don't even, maybe that's considered 0 hops. I don't know the technical correct terminology on a network hop, but everyone can talk to each other. Let's even just say, over Ethernet. And of course, really we're not going to just be sending Ethernet frames at each other, right? We're going to still be speaking IP. We're still going to be speaking TCP, but we're all on a local network. So for example, let's say we have some private network, and we're going to call it the 10.0.0 star network. Or maybe, if you prefer, the 10.0.0.24 network, as in the first 24 bits, the first 3 bytes are this prefix right here, and this guy can be anything, right? So this network right here. And let's say we have host A here that's got some IP address of, let's say, 10.0.0.2, And we'll say we've got host B with 10.0.0.3 and host C of 10.0.0.4. And again, I think I kind of talked about this in my last office hours. How the heck do they get these IP addresses assigned to them? Well, we're just going to ignore that problem for now. So there's a technology called DHCP, which is basically a mechanism for getting an IP address assigned to you. So maybe it happened through that, or maybe someone came in and set up the network and statically assigned these to each host, etc. Okay, and then one further thing we're going to say to kind of define what the heck is host A. In your head, maybe just think host A is one laptop at some Starbucks, host B is another laptop at some Starbucks, and host C is a third laptop at some Starbucks or some Wi-Fi network. It really doesn't matter. But let's just, for now, we'll say a simple, well-behaving, basic network. There's really fancy things you can do. In reality, something like the ASU network, when you're all on this kind of like local network, really all of these devices on the ASU local network aren't able to communicate with each other, even though they're kind of like on this single network. There's technology that allows it to basically mean these guys still can't talk to each other. So we're just going to say a simple network. Whatever you've got at your house or your apartment probably behaves in this way. Okay, so we're going to say that this host is just some laptop. It's got this IP address on this network. And it also, let's say, has some MAC address. So we're going to keep it real simple. 456. We're going to say it has this setup. Camera like shakes. It's so sad. And then this. Okay, so we've got an IP address. We've got a MAC address. Cool. So let's say that I show up to your apartment or your house or whatever, and I log into your Wi-Fi, right? I know the Wi-Fi password. How do I know it? Who knows? Who cares? I know it, right? And I am going to be host H for hacker, right? And I show up to your network and I am connected. So what does it mean to say that I am connected? Well, really all it means to say that I am connected is that there is a way for all of these people to talk. So when I join your Wi-Fi network, there's some technology going on there that allows for all of these things to talk. And let's say that I just, do whatever my laptop does, my kernel. So I'm running a MacBook. So my Mac OS operating system, it knows how to join a Wi-Fi network given some password. Again, that's a different discussion. It knows how to do this. And because my kernel is very smart and knows how to speak this world of, networking stuff, I connect up and my laptop just goes ahead and assigns me an IP address. We'll just say I get .100. And I guess H is not a hexadecimal digit, so I will give myself the MAC address of 4s. I like 4. Cool. So I've got this MAC address, and that's just kind of baked into the hardware. My kernel knows how to do its thing and get an IP address after I, come up here in the top right and I hit join this Wi-Fi network, and it joins the Wi-Fi network, and I get an IP address. Cool. Okay, so now we got 4 hosts sitting on here. And let's say maybe these are 3, well-behaving, well-mannered hosts on the network. And then there's me who connected up to the network, and I want to mess with this network. So let's say that I know that host A is talking to host B, right? So what does that mean? Let me just double check the chat, make sure. Yeah, you're connected, you're in, exactly. Host A and host B are talking, and I'm host H, and I really want to see what the heck are they talking about. So maybe, I don't know, you could imagine any level of sensitive information going on here, going between these 2 hosts. So for example, maybe we say that host, what is it? Host A, I'm trying to think of like a good fun example. I don't know. I'm crazy and I run, this complicated password manager thing that's a computer sitting on my network, and host A, well, does that even make sense? I don't know. Who cares? We're not going to try and sit here forever and think about the example. Um, host A and host B are talking. So what does that mean? So what that means is, let's say they're talking over, I don't know, TCP. So host A goes and says, SYN host B, right? And how does that happen? Well, the very first thing that needs to happen, right? So I'm basically saying, we're getting ready to establish a TCP connection with host B. Well, what's the very first thing that needs to happen? So host A, when it wants to go and SYN to host B, that's, of course, the TCP layer. Before we can even get to the TCP layer, we need to handle the IP layer. And of course, to handle the IP layer, we need to handle the Ethernet layer. It's a stacking thing. Before I can connect up, so let's say that host B is running some service on port 80, right? Host B is running a web server. And I want to connect up to that over TCP. So what we're going to say is that host A knows they want to talk to host B, and somehow, again, we're leaving out some details, somehow host A knows host B is 10.0.0.3, right? Host A knows really what they're saying when they say they want to talk to host B is what they're saying is that I want to talk to 10.0.0.3. So maybe this idea of host A, host B, host C isn't really a thing. Really all that exists here is IP addresses. So, there's networking has all these layers. Maybe instead we talk about how DNS allows us to resolve some, English looking name into an IP address, but we're not going to deal with that layer. Host A wants to talk to 10.0.0.3. So let's even just kind of ignore this host A nonsense. So 10.0.0.2 wants to talk with 10.0.0.3, right? 10.0.0.2 then wants to send some sort of SYN packet to 10.0.0.3 to start the three-way handshake with 10.0.0.3 to speak TCP, which means 10.0.0.2 knows they want to talk to 10.0.0.3. Why do they know that? Because, well, we're literally just defining it as 10.0.0.2 wants to talk to 10.0.0.3. They know they want to talk to 10.0.0.3. Here's the issue. In order to send that IP packet, I need to encapsulate it in an Ethernet frame or an Ethernet packet. Kind of in the world of Ethernet, it's maybe more common to say a frame. Call it a packet though. Whatever. Doesn't really matter. Okay. I know that I want to talk to 10.0.0.3, but I need to encapsulate this in an Ethernet packet. Ethernet packet has 3 fields to it. It has a source MAC, it has a destination MAC, and it has a protocol. So we know that the protocol is going to be IP, right? We know that for sure. And we know the source MAC address. That's also very easy because I am 10.0.0.2. And so I know how my stuff is configured. I know that I am on this AAAAA whatever nonsense thing. The tricky thing here is that I don't know my destination MAC address. I know that I want to talk to 10.0.0.3. 10.0.0.3 is not a MAC address. This is not a MAC address. And I don't magically know that it's BBBBBBBBB as the MAC address. We, of course, looking at this diagram, the setup, we know that that's who I want to talk to. But I don't know that. All I know is I want to talk to 10.0.0.3, and I don't know who the heck that is. So one option is to say, well, screw it. I'm just going to send it to everyone. Okay, everyone that I'm going to reach by Ethernet, I'm going to broadcast this out. And now this is going to, now I can put an IP on top of this, and I can put TCP on top of that. But what's going to happen here is that this is now going to be broadcast to everyone. This is the broadcast MAC address. And so the physical device, right, the switch on the network that literally connects these four things together. If you want to keep it simple, imagine you literally have this physical device with like 4 Ethernet cables coming out of it going into each laptop. Right? We have 4 laptops, 4 Ethernet cables, and they're all literally just plugged into each other. And it's this switch. When that switch sees FFFFF, what it's going to do is it's going to come, this packet is going to show up into the switch, and the switch is very simple, and it sees FFFFF, and it's literally just going to shoot the packet out down every stream. So we just kind of like multiplex that. We broadcast it out. So that is an option, because on top of this then, right, I'm going to have some source IP address. So this is, this is our Ethernet layer, and then we've got a IP layer sitting on top of this. So I need my source IP address, which, very easy. I know that. Got a destination IP address. I know that because I know that I want to talk to 10.0.0.3. I know who I am, that I'm 10.0.0.2. Of course, there's other fields in IP. For now, we'll just say that there's a protocol field. Refer to the slides. There's more fields in here, but we're going to ignore those for right now. And we're just going to say, look at the protocol. And we're going to say, hey, the protocol says it's TCP. So we go ahead and we'll keep that here. We'll stack TCP on top of this, right? These are all just sequential bytes. So we got a bunch of bytes for Ethernet, a bunch of bytes for IP, a bunch of bytes for TCP. So we know source port. Well, maybe you say we don't know our source port, right? I know that I want to talk to port 80. What the heck is mine? Well, my operating system is going to take care of that. It's just going to decide, well, you know who you are. You're running on port 42123 or something, right? It just picks an unused port and says, okay, well, that is going to be what we're going to use as the client connecting up. We know the destination port because, again, the statement of what I'm trying to do is I'm 10.0.0.2 wanting to talk to 10.0.0.3 on port 80. So we got our destination port, and there's more flags for TCP, but we'll just go ahead and say that we're doing a SYN packet as part of my flags, right? So this is the packet that I'm sending out. It's literally going over this Ethernet cable, showing up to this switch device, and this switch device is just shooting it out into every single Ethernet cable because it got the broadcast MAC address. Cool. So now what happens here is everyone receives this packet. Now, under well-defined, well-meaning, good-intentioned people, our kernel is actually going to reject this. Just about everyone is going to reject this. 10.0.0.4 is going to reject this. Me as the hacker, my kernel by default will also reject this packet, and I will never even see it. My kernel will see it, and then it's just going to throw it away. But 10.0.0.3 knows that, hey, I am 10.0.0.3, and the kernel is going to say, okay, well, I'm 10.0.0.3. Let's not throw this packet out. This was meant for me. And it's going to go and say, all right, well, let's walk through my bound list, right? So basically everyone that called the bind system call, right? People literally bind to something like port 80 is going to say, okay, what process bound to port 80? Did a process bind to port 80? If no process bound to port 80, what's going to happen here is the kernel is going to automatically reply with a packet because it's 10.0.0.3. This is just the kernel is just doing this for us. Okay, user space isn't taking care of this. The kernel is going to just reply immediately with a reset packet. It's going to be like, what do you mean port 80? Like, I'm 10.0.0.3. I know what you're talking about there, but we're not listening on port 80. We're not doing that. Why are you talking to me on port 80? That's not a thing. Reset. Go away. Like, that's not a thing. You're doing something wrong. I don't know what you're trying to do. There's no port 80 here. But it is 10.0.0.3. However, if someone did do the bind system call, then it queues up the packet, and it basically just waits for someone to do a read system call on that socket. And as soon as someone does a read system call, right, maybe we've got data on top of this, maybe specifically, it's HTTP data, but, it kind of depends what the heck's on top of here. We're saying it's port 80, so probably this client is sending HTTP data now on top of this TCP, right? And we've got some like get HTTP 1.0 piece of data. The read system call just receives this part. We don't need all these bytes here, right? These are bytes meant for the kernel. Even though this packet went out, right? Our user space program doesn't care about this. We do the read system call. All we get is this. Okay. Hopefully this all makes sense. No questions there. So hopefully it all makes sense. This is a bad idea though. This is not good, because here's what's going to happen. We did a broadcast packet. Me as the hacker, let's say I want to intercept this. Maybe we're not even doing get slash. Maybe we're doing post slash login. And it says username equals admin and password equals super secret, right? If me as the hacker can get this data, right, we kind of win, right? Or win in whatever definition of the hacker's objective is. But I'm sure a hacker might love seeing this piece of data show up. And guess what? The hacker does receive this, right? As we said, the destination MAC address is FFFFFFFFF. This is going to everyone. So my computer here is going to get this packet. Now, of course, I'm running a MacBook. My kernel is going to get this packet. It's going to automatically reject it. But that's just because of my kernel that I'm running, right? I could be running the hacker kernel that just doesn't throw away any packets and instead logs them to a file or something. Or I could roll up into my computer and literally just assign an IP address. I could say, for example, let's actually maybe make this more concrete. SSH dojo 1, 2, 3, 4, 5, 6, 8, 9, 10. Maybe we should also zoom here. 1, 2, 5. I can, for example, if we do challenge run, and you'll see I got my demo code running, whatever. Actually, that's going to get annoying. Emacs Q. Let's make it not print that every 5 seconds. I can just show up here, and if I do IPA, I can see, hey, my IP address is 10.0.0.2. So if I'm the hacker, right, I don't even have to run some fancy, complicated kernel. I can literally just roll up here and say IP adder add 10.0.0.3 dev eth0. And look at this. Now I got 2 IP addresses. At this point now, my kernel is going to do what I said, right? So now I'm kind of got 2 IP addresses. There's no reason you can't have multiple IP addresses. I mean, probably, I don't know immediately off the top of my head why you might do something like this. On 2 IP addresses on the same interface, I'm sure there's a real use case for it, but it doesn't matter, right? This is my computer. It's my host. I do whatever the heck I want to do. Now I've instructed my kernel to not throw this packet out. So now if anyone starts talking to me and I get this packet going to everybody and I'm 10.0.0.3, well, guess what? I receive that packet now and my kernel doesn't throw it out. And so if I'm sitting here and I also write, netcat listen 10.0.0.3 port 80, I'm now listening. If I get this packet that's sent to the broadcast MAC address and this shows up to 10.0.0.3, even though I'm not really 10.0.0.3, I mean, what the heck does really mean? I'm going to receive this packet and I'm going to see now this post with the /login username equals admin, password equals that. So this is, not really it. This is not the way to do it. And it's not even just like a a security thing, right? It's also just like a performance thing, right? Do you really want to be broadcasting packets to everyone on this network? Like, why? Why do this? Like, is that really your intention? Yeah. So think about it like that. Like this isn't really the purpose. The purpose is to have a destination. The destination isn't always meant to be everyone. There's a time and a place though for broadcasting to everyone. And one particular time and place for that is in the world of ARP. ARP is another protocol. So we've got IP, we've got Ethernet, we've got IP, we've got TCP. And ARP is kind of like a little helper protocol. And it sets up the glue between destination MAC and IP address. So really what's going to happen here is not this. Under a well-behaved normal operating system, the kernel doing all of this stuff, right? I run curl 10.0.0.3 http://10.0.0.3. My operating system isn't going to do this. It's not going to broadcast this packet out. Instead, what it's going to do is it's going to say, actually, we'll do this. Oops. We'll grab this, right? I need to encapsulate it in an Ethernet packet. I want to talk to 10.0.0.3. Who the heck is 10.0.0.3 Ethernet edition? Right? What's their MAC address? And this is where ARP comes in. So maybe I already know it. I have this ARP table that like saves the associated MAC address. I go and look up in my ARP table, and let's say this is the first time trying to talk to 10.0.0.3, and I say I don't know their MAC address. So what I do is I create an Ethernet packet. Okay, so we go Ethernet, and we say source is AAA, destination. Well, actually, I got rid of that. Oops. Hold on. Let's keep this. Actually, this is looking good. We do actually want to broadcast this out. We're trying to find them. And so our protocol, though, is not IP. It's ARP. And so instead of on top of Ethernet having IP, well, no, we've got ARP now sitting on top of Ethernet. And so what we need is some fields for ARP. And ARP has a few fields. One of those fields is the type. So there's, for our purposes right now, we're going to say it's the who is type, which is basically, this is the question, like, who the heck are you? I'm trying to figure this out. I'm going to say that my, then we have 4 more fields. We have a source, or is there 4 more fields? No. Hold on. Let's go to the slides. Don't want to mess this up. I know what information needs to be conveyed. Now I'm just thinking, how the heck is it conveyed? This. Okay. Right. We have we call it an operation. Okay, let's say operation. Okay, and that is who is. Now we have 2 types. So there's a whole bunch of stuff. Okay, you know what? We'll include it all. We got hardware type, and we've got protocol type. Realistically, I mean, I've only ever seen this with Ethernet and MAC, but what that is the hardware type is, you know, Ethernet, protocol type is IP. And then we've got, well, we'll do it in order, sure. Operation, who is, and then we've got 2 sources and 2 targets, or 2 senders and 2 targets. We've got sender hardware, which of course being this guy is this, and sender protocol, or to call it that, yeah, I guess it's address. It's basically what you would expect it to be, right? My sender, this is my MAC address, this is my IP address. And then we've got a target hardware address, and we don't know what the heck that is, right? We can just say, fill that in with zeros or something, right? It's going to be some sort of bytes. I don't think it really matters. And then we've got our target protocol address. And this is important. This protocol address is important. It's 10.0.0.3. All right, so this is how we ask who the heck has 10.0.0.3, right? This is like the fill in the blank guy. And I send this out and we're broadcasting it. So everyone on the network receives this who is packet. Let's assume everyone's well behaved, well mannered. 10.0.0.3 receives this thing and says, hey, that's me. I'm 10.0.0.3. Let me go ahead and reply. So it replies. It does the following. It replies with an Ethernet. It replies with a source MAC of BB, right? It replies from itself because we're assuming this is well mannered. It knows who we're talking to as well, because guess what? It's in here. Sender hardware address is in here. It's also in the Ethernet frame itself. Probably these two things should match up. Unclear what the heck the kernel is going to do if they don't match up. I don't know. I'm honestly not sure. You have to experiment with that for how normal kernels implement that. Our protocol is still ARP. We've got Ethernet. We got IP. Our operation is no longer who is. It's now is at. And who the heck am I? I'm B456. I'm 10.0.0.3. I'm talking to AA and talking to 10.0.0.2. And now this has been replied with. And so, because of this information, this is going to show up because it's destined to me, the person who asked. You could also, in theory, broadcast the response to everyone. Maybe you want to like gratuitously say on the network, like, hey, I'm over here, in case someone else wants to ask. And now someone else's kernel receives this and like, oh, let me save that for later. That's good to know. I didn't ask, but you know what? That's good to know that this is the IP address, MAC address pairing here. And so now, critically though, the sender hardware address is read. The sender protocol address is read. We know this is an is at, and so I can pair these two things together. So now when we go back to this example, when I wanted to do this, right, I wanted to send all of this. If I do this ARP thing before, now I don't have to broadcast this. Now I know who I'm talking to. Okay. Cool. So that's what's going on there. If there's any questions, feel free to ask in the chat. Hopefully, though, it's very clear that there's a little bit of everyone's playing nice feeling to all of this, right? We keep saying, assuming everything's well behaved. When I receive this packet here, right, I get this. If I'm the hacker and I want to, like, remember the initial issue before was, I could see this password here in here because it was being broadcast to me. And since it was broadcast to me, the packet is literally showing up at my device. I can do whatever the heck I want with that packet. Now it's not being broadcast to me. Now I don't even see the packet anymore. It's only going to the quote unquote correct place, right? The genuine 10.0.0.3. Okay, well, what do we do about that? If I'm the hacker and I want to abuse this. So, I mean, it's probably pretty straightforward, right? Like, hopefully you're seeing the issue here is that I received the fact that 10.0.0.2 is looking for 10.0.0.3. If I'm trying to play as 10.0.0.3, all I need to do is reply, right? So I'll just say, instead of BBBBB or whatever, right? I put my hacker source MAC address and I fill this in for myself, right? And I just say, hey, you're looking for who's 10.0.0.3? Guess what? It's me. And it's that's what happens here automatically for us. If we assign 10.0.0.3 to this interface in the Linux world, as soon as I get a who has packet being sent to 10.0.0.3, my kernel is automatically doing this for me now, right? It's saying, hey, 10.0.0.3 is me. It's at this MAC address right here. Talk to me. But you might say, well, now what? I need to wait for for 10002 to ask who the heck is 10003? Well, the answer is no. I can just send this out whenever I want. This is at least how the Linux kernel that we're running for these challenges works. You could imagine implementing this however you like. But the default implementation here that we're using is if a kernel ever receives an is at packet, it just updates its ARP cache, its ARP table, and says, okay, well, 10003, if I ever want to talk to them, send it to this MAC address. Boom, done. It doesn't even say like, oh, but did I ask who that is within the last 5 seconds? No, we don't do that. We don't have any statefulness to it. Really, all that matters is this is at packet. This who is to like instruct someone to tell me. But if I ever receive an is at, I'm just updating. This is now the truth. So what that means is that if I want to receive this packet, like I know, for example, that 10002 and 10003 are talking, and that pretty soon, 10002 is about to send a login request, HTTP request off to 10003, I can just send an ARP packet that has this information. I just send this ARP packet, and suddenly it's updated. So let's quickly go ahead and actually do that rather than talking just theoretically. Okay, wait, maybe we've got some questions. So that's how you, yeah. So I mean, I guess to clarify, we're not necessarily a man in the middle yet with this convention, right? It's not just sending this packet. There's kind of another step that needs to happen here, which is, I guess there's kind of a thing that's, I just am now realizing this isn't so accurate right here, right? This is not a valid TCP packet. We would never do a SYN and attach data to it, right? We need to complete this three-way handshake. So I can tell 10002 to start talking to my MAC address when it wants to talk to 10003, but I also need to complete this TCP handshake, which is totally fine, right? As long as if I receive this SYN packet, I need to send a SYN ACK back, right? Following TCP correctly, it's going to send an ACK back to me. And then the fourth packet is going to be like a push ACK packet, right? And that push ACK packet is going to contain this data. So I also need to complete the three-way handshake. And even still, I'm not a man in the middle at this point. I am just like, I'm now just spoofing. I have become 10003. If, for example, there's like, it kind of depends on what your goal is here, but maybe there's not anything sensitive yet. Maybe maybe I don't just care about the username and password. Maybe I care about the response of this HTTP reply, right? So maybe, for example, I care about the fact that we're going to get HTTP data back, and maybe it has HTTP 1.0 200 okay, and it has the message super secret. This is even more secret and scary to leak, right? I care more about the reply that the server is going to send. Well, I mean, in this case, because of the nature of HTTP and the fact that HTTP is stateless, right? At the point that I've captured the username and password, we're good to go. So now let's just go talk to the real 10003 and make a login request with these credentials, and presumably this is going to get sent back to me. But there's also times where, you might have a not so stateless protocol where we can just capture the username and password and then kind of go do our own thing later with that. Maybe we truly want to continue on, right? So maybe there's a different protocol. Instead of HTTP, maybe it's like a different protocol where it's like the data that it sends is something to the effect of, I want to log in. And we get a response back saying, okay, what is your username? So maybe actually let's do like, I want to log in. And 3 talks back and says, okay, what is your username? And then 3 says, or then, I guess we're not swapping that around. Then 2 says, my username is admin. And hopefully, I don't know, you see that we got this back and forthness, right? We got this TCP conversation happening. And it says, okay, what is your password? And it says, I keep doing that. We're making this, hold on. My arrow drawing is difficult. Okay, my password is super secret. And maybe I don't want to literally just capture that very first thing, but I want to capture this whole back and forth thing. Well, if I just become 10003, I receive this message and it's like, now what? It's like, maybe they're speaking some unknown protocol and I just want to capture everything passively. I want to passively capture everything. And I receive this packet and then like, well, now what, right? Like by default, let's say they're talking over port 42, all over port 42, and I've got my simple little operating system running and I have nothing bound to port 42. And now, 10003 sends off to 10002 a reset, right? TCP reset packet. And it's like, now I haven't received, like I haven't witnessed what was going to happen later. Like, I don't know what the heck. Okay, cool. You want to log in. So what? It's like, what should I do? Should I do a reset? Or, in that HTTP example, you could imagine, well, okay, then I'll just send HTTP 1.0200. Okay, should I send that? Well, I mean, this isn't even HTTP. Why would I send that? It doesn't make any sense. Why would we have an HTTP response to this? I mean, what should I do? Well, if we want to talk about man in the middle, the thing we do now is, so we'll kind of, it's kind of hard to say what is 10003, right? So we'll say maybe H for hacker, right? We'll just add like an extra meaning of like, which 10003 are we talking about here, right? The real genuine guy or the hacker guy? Well, in this case, the hacker guy gets it because we set up ARP in this way where it's going to the hacker because I told 10002, hey, 10003 is at this hacker's MAC address. So I get this packet. And now what do I do as the hacker? Do I send a reset packet? Do I send some random HTTP reply? Well, if I want a man in the middle, what I do is I go and say 10003 hacker could talk to, the real 10003 and say, I want to log in. And this might create an issue because 10003 is talking to 10003. It doesn't really matter. I could also be, as the hacker, 1000100, right? I can send packets however the heck I want to send packets, right? Like, even though, in user space, you're not normally sending these packets, it's coming out of your physical machine. Like, if you had to, you could write your own kernel to like send packets. Fortunately, the Linux kernel allows you to send raw packets. And one of the tools we use in this class for doing that is Scapy. Scapy allows you to send these arbitrarily set up packets. And so this is what I do, right? I get this as the hacker. And now I just do the same thing. I say, I want to log in. And 10003, the real edition, says to 1000100, and it says, okay, what is your username? And now, as 10003, the hacker, I can go and talk to 10002 and say, okay, what is your username? Right? And so you kind of have like this double repeating nature where every time I get a packet, I send it to the real guy. And then every time the real guy talks to me, I send it back to the victim, right? So there's this duplication of packets. And of course, this is just showing it at the data layer. You would also have to duplicate all of these, right? At the TCP layer, we would also have initially received not a I want to log in, I would have initially received a SYN packet. And so what else would I have to do? Well, I would have had to set up as 10.0.0.100 or, 3 or honestly, you know what? I'm saying 100. Just be 2. Just make yourself also be 2. You can be 2 and you can be 3 as the hacker. You be whatever you want, right? Like, sure, become 2 as well. Then, you're going to have to send an ARP reply is at off to 10.0.0.3, convincing 10.0.0.3 that you're also 10.0.0.2, right? You're just like telling everyone, hey, I'm who you want me to be, or really who I as the hacker want you to think that I am. So now we do this, right? And we'll say this is as the hacker, right? Instead of maybe as 100, because why do we have another IP address show up? Well, we don't have to do it that way. We got the real guy and the real guy. We don't even need this 100. Or you can do the 100 game also. It doesn't really matter. And I now need to say off to the real guy, SYN, right? I need to do this handshake also. So the real 2 talks to the hacker 3 and says SYN. Well, then the hacker as 2 will send to the real as 3 a SYN. And hopefully, I feel like it's kind of a little bit confusing that there's double IP addresses going on. Like one's the real, one's the hacker. Hopefully you've got some idea what I'm saying here. It's literally like just send these packets. Put as the source MAC address, whatever the heck you want. Put as the source IP address, whatever the heck you want. And you're good to go. And then also, the real 3 is going to send back to the hacker 2 SYN ACK. Because guess what? The hacker 2 just sent to the real 3 a SYN. So according to TCP, the 3 real better send to 2 hacker a SYN ACK, because if you get a SYN, you better send a SYN ACK back, assuming you're handling that port, of course. Otherwise, you'd have got a reset packet, and you could forward the reset packet instead. And then, what do we do here? Well, I say 10.0.0.3 as the hacker sends to 10.0.0.2 the real guy a SYN ACK. And so all of these packets are duplicated. We just need to forward them along. And in doing so, now, since we're duplicating things, right? Like if I want to decide how the heck do I respond, well, I'll respond however the genuine guy would do it, right? If the genuine guy does this, that's what I'm going to do. That's how I'm going to respond. And so now in doing that and acting as both participants of the genuine, but sitting in the middle and making sure the traffic flows through me, now that's where the man in the middle comes from. We just reestablish with each genuine side and talk to them as if the other person talked to me. And, however the other person responds, I just forward that along to the other guy. However this person responds, I forward along to that guy. And we're good to go. We're man in the middling now. And at any point, like you could deviate, right? This is all just the decision to mirror this interaction. As soon as I got this, from 10.0.0.2 saying the real thing, or, let's say as 10.0.0.3, the real guy said, okay, what is your username? I decided to mirror that. Instead, I could have sent, okay, what is your super secret password? Only I should know, right? And then this is no longer just a passive man in the middle. Now I've deviated. Now I'm doing my own custom logic, I don't have to just mirror. I can at any point deviate from the conversation. And now, if 10002, the real guy, is saying, well, you know what? I trust 10003. That's a trustworthy guy. I'm willing to tell 10003 my secret password only 10003 should know. Well, maybe now 10002 decides to say, oh, well, this is my password. It is don't tell anyone. Exactly. Hopefully it's clear what I'm saying here with this. It's kind of all what you want to do with how this all works. And the reason that 10002, again, just to really hit this home, because maybe you're like, well, yeah, if I could just do this, that sounds awesome. But how the heck do I do this? The reason that the real 10002 is going to talk to the hacker 10003 instead of the real 10003 is because me as the hacker, I sent one of these guys. I sent an ARP is at. In this case, I'm telling 10002 that if you ever want to talk to 10003, talk to this MAC address. And this is where it's like the genuineness breaks, right? This is not the real 10003's MAC address. This is my MAC address. And similarly, I could do this and send this off to, I could talk to 10003, right? So in this case, I'm talking to 10002 and saying, hey, if you ever want to talk to 10003, you better talk to this MAC address. Similarly, I could say, hey, 10003, if you ever want to talk to 10002, guess what? It's this MAC address. Now 10003 thinks that 10002's MAC address is this, and 10002 thinks that 10003's MAC address is this. And guess what? Now 2 thinks that 3's MAC address is my MAC address, and now 3 thinks that 2's MAC address is my MAC address. And so whenever the real 10002 wants to talk to whatever the heck 10003 is, they know the MAC address because I sent them the MAC address. And so that's why it's going to show up to me instead of the other person. And I guess to kind of maybe even further go along with this, you don't send an ARP request every single time you want to talk. You consult with your ARP cache. And maybe your ARP cache associates that IP address and that MAC address for 5 minutes, right? It could associate this pairing for 5 minutes. We can trust it for 5 minutes. After 5 minutes, I don't know, maybe something changed on the network. Maybe 10002 is now a new person who's taken on that IP address that's at a different MAC address. And so maybe every 5 minutes, I'm going to send out a who has packet, and I'm going to clear out my cache, and I'm going to refigure out who it is every 5 minutes. Well, if that's the case, just send this is at every 5 minutes, or like every 4 minutes and 30 seconds, so that it never tries to ask. Because guess what? The real 10003 is also going to send with the genuine thing. So it's going to kind of get both is at, and it just depends on how it's implemented. Turns out the way it's implemented is whatever the latest one to come in, that's who we're going to be sending to. So to maybe ground this a little bit, how do I do my cache? So you can see, for example, I ran ARP VN. I've got 0 people in my cache, my ARP table. If I go and I say netcat 10003 on port 80, right? So I'm 10002. I'm going to talk to 10003. There is a 10003 out there. They're not listening on port 80, but it doesn't matter. That's a TCP thing. But first, we got to deal with IP. In order to do IP, we need to know the MAC address. In order to do that, we need to know what is 10003's MAC address. I run this, so of course it fails netcat. It doesn't actually connect up, right? If we do echo this, it says error, we didn't succeed. But now if I go and do this, oh boy. What? Oh, we got an issue. I gave myself 10003. So the kernel is smart. It says, I don't need to do that. I'm 10003. I'm not going to send out an ARP request. Why would I do that? I know where 10003 is. Hold on. IP adder del 10003 dev eth0. What? Okay, cool. Deleted it. Oh, it's /16. Whatever. Cool. So now we got this. We got this ARP table. Okay, now if I netcat off there and I look at this ARP table, look at this. Now we've filled something in. And again, all of this is just like, the kernel is just a program that knows how to handle the state machine that is IP and ARP and Ethernet. And it's just like doing what it thinks it should do, right? However, the kernel developers wrote this thing. And hopefully they wrote it in line with, how this all should behave. Well, look at this. I've got now in my ARP table, I've got 10003, this 80 again, this is a TCP thing. This question of ARP is an IP question. It's an IP Ethernet pairing question. So now we know that 10003, the hardware type Ethernet, has this hardware address. So if I ever want to talk to 10003, I'm going to be sending it over this. And in fact, if I do tmux real quick, and I do TCP dump I eth0, and I do ARP ARPVN. Oh, did it already clear that? Really? Interesting. Okay, well, whatever. Ping 10003 port, or netcat 10003 port 80. Look at this. Our kernel just sent an ARP packet saying, who has 10003? Tell 10002. This is kind of how we write it out. And 10003 came back and said, 10003 is at this MAC address. And so now, again, if we do this, we see that it has this hardware address. And interestingly, you can see also that, so once we got through this ARP, we send out an IP packet, specifically TCP on top of that IP. So we can see we're sending as 10002, the kernel assigned a source port. We're talking to port 80, because again, if we look here, what did we try to do? We tried to talk to port 80. And it sent a SYN packet. Why did it send a SYN packet? Because guess what? We're starting a TCP handshake. And, it has this sequence number, et cetera, et cetera, et cetera. Length 0, there's no content on top of it. You don't put content. What did 10003 send me on port 80? It says .http because TCP dump's being fancy and saying, it's good. It's trying to be nice to you. You could disable this. I don't know off the top of my head how you disable this, like resolving to the normal associated service. But it says, well, 10003 on HTTP port 80 wants to talk back to this. And what are we going to do? Well, we're going to send a reset acknowledgement packet. Why? Because 10003 doesn't have something bound to port 80. So it says, what the heck are you doing? Go away. And I guess this is a little bit surprising to me, but it's however it's implemented is how it's implemented. It looks like also 10002 became interested in figuring out the MAC address of 100, or 10003 also did an ARP request out for 10002, right? We kind of have the mirror. Looks like, I don't know what induced this behavior, why suddenly it decided to do it, why it didn't just like take the information from this who has request and just save that, because as soon as you get a who has, you also know now who 10002 and what their MAC address is. I don't know, for some reason, whoever implemented this networking stack decided we're not going to do that. And so at some point, 10003 also decided to send out an ARP request. And you know what? 10002, that's us. Again, we didn't do anything. 10002, our kernel automatically did it for us. It sent this out. Now, again, if we look here, looks like our ARP cache is configured where, I don't know, maybe it's 60 seconds or something, 30 seconds. I don't know. We could time it. It looks like now if we wanted to talk again to 10003, we have to send out a who has. Now we've got it in the cache. We go here and we netcat again. You'll see we didn't do another who has because it's still sitting in the cache. And I really don't know how long it sits in this cache for. It's up to the operating system to have determined its policy there. You could send an ARP who has every time if you really wanted to for every single TCP handshake. Or you cache it for 30 seconds, or you cache it for 5 minutes, or you cache it for 2 hours. I don't know. It's up to whoever implemented this networking stack. Okay. Let me think here. Okay, let's first see this. We really do a manual three-way handshake to connect host A. Yeah, exactly. The first step is sending these is-at packets. If you want to get in the middle of two people communicating, you need to become who they're looking for. At some point, if you're interested in man in the middling 10002 and 10003, you better convince each of them that you're the person they want to talk to. Because, if we have 10002 and they want to talk with 10003, they're going to be sending ARP who has, right? If they don't know who it is, they're going to say who has. If they do know who it is, if the hacker sends off saying is at 10002, 42, 42, 42, 42, 42, 42, or whatever. Yeah. And it also says .3, if we broadcast this out to everyone, now they're not going to send these who has packets because now these two know who this is. So now, we're kind of, as a result, and it's confusing to do this just, so let's say, this is where we're going to bring back in host A, which is maybe like ground truth, of who the heck this is. Now, when this is happening, we've got this setup, which is host A, host H, except I'm trying to think about how to diagram this, right? Host H kind of has become both, just depending on this. And then host B, right? So in doing this, this is kind of the result. And of course, you see 3 twice because, which is which. If we go to the true, what does it really mean to be this person, the correct identification, whatever correct means. We got 3 physical devices on this network or whatever. This is how this is going to happen. And so because we've convinced A that this person right here, or maybe this host, really means our MAC address, right? 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. Right, maybe this genuine thing is the MAC address, right? We'll do that. Right, now this is how we've kind of established this. Because I have convinced host A, this person here, that if they ever want to talk to 3 or 2, obviously if they're going to talk to 2, their kernel's probably not going to listen to this. But their kernel, there's nothing in the kernel that's happening that's setting off red flags like, hey, wait a second, I'm 10002. Why the heck is this person telling me that they're 10002? I should start panicking. kernel just doesn't do that. You could imagine implementing a kernel that does like pop up a notification to the user saying like, hey, sketchy stuff is happening here. I think I'm 10.0.0.2 and someone else just tried to tell me that they're 10.0.0.2. We should start panicking here. It's just that doesn't happen, at least under this default kernel that we're using here, which is just, default normal configured Linux kernel. Probably there's security hardened things. In fact, I'm pretty confident that there's security hardened things that don't listen to these. It's called like a gratuitous is at. You could imagine the feature of like as soon as you join a network, rather than waiting for everyone to slowly ask who has this IP address, you could just like as soon as you join the network, just is at to everyone. Just hey, let them know, hey, I've joined the network, I'm here. If you ever want to talk to this IP address, here I am. And you gratuitously is at that. You could harden things though, where you know what, I'm not respecting a gratuitous is at. I'm only going to respect things within 5 seconds of doing a who has for that. Of course, does that really solve the problem? As a hacker sitting on the network, I could just wait for a who has and race the person depending on how the protocol is, just be quicker than the real one to send the is at. I could start doing denial of service things against the real guy to make sure they never are successfully able to send an is at. Hopefully you can imagine that this is the hard problem, right? It's kind of a lot of built-in trust to the protocol that everyone's kind of just doing what they're supposed to be doing correctly here. And that's why it's so abusable. Then you can go to doing the manual three-way handshake. Exactly, and then you can just forward it. So one thing I will say about how things are configured here, how do I figure this out? Syscontrol IP proc sysnet IPv4 IP forward. This thing. This is just a configuration thing, and it's turned on. So this thing here, again, so this is a Boolean value, and it's kind of exposed to user space through this file, this fancy file. It's going to report either a 0 or a 1, depending on how it's configured. For you, this thing is configured to a 1, at least right now. We've kind of thought about setting it to be a 0 for these challenges. But how your system is set up, and I don't think, unfortunately, because of the infrastructure, that you can change this. Just the way it's all set up, there's no way for you to change this, I don't think. I guess I can try. Let's see. I do echo 0. Yeah, no, exactly. It's a read-only. If you were a true root on this system, you could change this. It wouldn't be a read-only file system. You could modify this thing. You can't modify it. Something to say about this flag in particular. This deals with the question of, okay, so I am host. Let's just be genuine here. No hacker host. We got host A, which is at 10.0.0.2. Host B, which is at 10.0.0.3. Host C, which is at 10.0.0.4. You can imagine the situation where host A sends a packet to host C. But this packet that they're sending at the IP layer, so maybe we go back to the, right, we'll say this. Protocol IP, source IP, and again, we'll say 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. And this. Okay. No funny stuff happening here. This could just truly happen. And maybe it happens because you broadcast it, or maybe something weird happens. I don't know how this happens, but just imagine that it could happen. And we're talking to 10. I am 10.0.0.2. I am talking to 10003, and the protocol is TCP on top. And we're not going to show the rest of the packet. Oh, and this is also not work. This is definitely IP. Okay, so something like this happens, and you're going to see that this is no good. This is a weird packet. So I said in one case that if something like this happened, right, maybe, again, let's just actually go back to the FFF case. But for whatever reason, so it shows up on C. It shows up on host C. So I'm going to actually go back. Make it real crystal clear that this is showing up on host C. Okay, host C receives this packet. It says it receives it because, this physical thing that's routing these Ethernet frames says, okay, C, this is this Ethernet cable, push it through there. And you might think, how does the switch know to push it through the right thing? It's also doing smart things where it's figuring out, well, if there's ever a source MAC address of CCC coming through here, well, I guess if there's ever a destination, I should probably go down that cable. There's lots of layers to all of this. The switch just knows what it's doing. Let's say that. So I say go to CCCCC. It shows up on host C. Host C says, cool, I got this packet, but I don't know what the heck you're doing. I'm not 10003. You've got a choice here as 100 as host C. What do you do with this thing? So I previously said, well, let's just drop the packet. Okay, I am 10004. I'm not 10003. Drop the packet. It's not meant for me. No one needs to ever see this. Just delete it. Get rid of it. There is a different option though, and that different option is for host C now to do the following. Ethernet. I'm actually not totally sure what the source MAC is going to be. But let's say that C knows where the real B is. It knows how to route that. It knows that B is really over here. And I'm trying to think about this. I bet it will correct this. I'm not totally sure if it's going to leave the AAA intact. It's probably actually going to make this genuine, right? It's probably going to not send on behalf of AAA. That would probably be weird. It probably does do this. Unsure of what happens here with this source MAC address here. I think we update it to be us. Pretty sure. But we don't need to change this. This is on an IP layer. This is what's happening. It really was 2 that wants to talk to 3. Even though I am host C and I'm not 2, this other option is to forward the packet. So that's what this is. IP forward, which in your case is set to 1, means that if I ever look at this, if I ever receive a packet and I look at this destination IP address and I say, I don't know who the heck you're trying to talk to, that's not me, but I know where I can find them. I know where the real 3 is because it's in my ARP table or it's in my routing table. Or it's in, I'm willing to send out even an ARP request to go find it for you. In this case, if we configure IP forwarding on, this is what happens. We forward the packet along, and now because we've set destination MAC to BBBBB, right, the IP protocol hasn't changed at all. The Ethernet has changed. I can get this communicating. And in this way, host C has now acted as a router, right? It's done this. Host A wants to talk to 4, or wants to talk to 3 rather. Host A says, I want to talk to 10003. It, for some reason, has sent that off to host C. And host C says, I'm not dropping this packet. I'm a router. I'm forwarding this. I'm going to forward this off to B. And in that way, now the packet has made it there. This is how routing actually occurs. You could do this as a nice thing to do or something, or you could think about your router at home, right? When I want to go and talk to google.com, who the heck am I sending that packet to, right? So let's say google.com resolves to 8.8.8.8, right? So get rid of DNS, get rid of the domain name. I want to talk to 8.8.8.8. Who do I send this packet to, right? I know I want to talk to this guy. What's going to happen here, to be kind of correct, is if we go back here, I'm going to notice that this interface, well, hold on. Let's go to a more normal thing. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, let's get out of that virtual network. Okay, we got three interfaces. We got a loopback interface, an ETH0 interface, and ETH1 interface. Okay, I look at this guy. This guy right here is willing to deal with this IP range. This guy right here is willing to deal with this IP range. This guy right here is willing to deal with this IP range. 8.8.8.8 does not fall into any of these IP ranges. So what that means is what the heck do I do? Like, this is a disaster. Like, I'm not configured to talk to anyone. Okay, this is where routing tables come in. If I ever get a packet destined for 10 dot something, I am going to send that through the ETH1 interface, right? This makes sense, right? This 10.011/8. If I ever want to talk to 10 dot something, push it into the ETH1 interface. Think of this as like a port, and then like someone else is dealing with it. It might be a switch, it might be a virtual thing. In this case, it's a virtual thing. Just push this packet into this port, into ETH1. If I ever receive something, if I ever want to talk to 172.18.***, push it into the ETH0 port. So, right, in one case, we send it into this port. In one case, we send it into this port. If I ever receive something destined for literally anything else, push it into the ETH0 port. This is just how it's been configured. This is our default gateway. And specifically, we're going to destine this out for this IP address. And this guy right here, this IP address right here, this host here, is going to know how to get it where it needs to go. And so that is kind of the whole idea of IP forward, is like, what do we do? So this guy right here better have IPv4 forwarding on, or whatever the equivalent is, right? It could be a physical device that has hardware doing everything. There's not even a Linux kernel or a kernel or anything. It could all just be done in hardware. But this guy better be forwarding. In your case, right now, I think we're going to change this maybe in the future because, I don't know, I'm thinking about what we like more. But right now, you are set up to IP forward. And so what that means, as a little warning, it is very applicable to this challenge, is since you have IP forwarding turned on, if you go and gratuitously send out these is-at packets, okay, you tell everyone that 2 can be found here, and you tell 3 that everyone can be found here. I come over here, I look at my IP address, and let's even make this real simple. IP adder del 10002 dev eth0, right? I don't have an IP address now, right? That's how we've set it up now. I don't have any IP address. I could add one again. And I receive this packet for 10.0.0.2, for example. Let's say someone sends a packet to me for 10.0.0.2. Because we have this IP forwarding thing set up, what is going to happen is you will receive that packet, right? Like if you use Scapy or TCP dump or whatever to investigate packets you are receiving, you've told everyone you're 10.0.0.2. If anyone wants to talk to 10.0.0.2, you will get that packet. But what's also going to happen is that you're going to forward that packet to the genuine 10.0.0.2, right? Your ARP table will at some point figure out where the heck 10.0.0.2 is. You're going to automatically forward this packet. So just keep that in mind. It's actually very convenient if you want to just man in the middle. and you don't care about changing traffic at all, this is super cool for you. Because remember how I said up here that like we want to do this mirroring behavior? If you want to do this mirroring behavior, as in not this part, right? We don't get to do that. If we want to do this mirroring behavior, now our kernel is going to do it for us for free. We send out these gratuitous ARP replies, and the real 2 is going to talk to the hacker 3. I'm going to get this, and I don't actually have this IP address assigned to my interface. So if I look IPA right here, I don't have 10.0.0.3 assigned. I could have sent out that ARP thing. I don't have it assigned. What's going to happen is my kernel is automatically going to go and take this from 2 and send it to the real 3. It's just going to forward it. It's automatically going to forward it. Same thing here. We get this, and it's just going to automatically forward it. It's going to automatically forward both sides, assuming you're getting both sides of things. And the only way you're going to get both sides of things is if you send out these isat packets to for both sides. So you send these 2 isats to everyone, and you're automatically going to start forwarding those packets, which is super cool if you want to passively man in the middle things. Less cool if you want to be able to do something like this. The simple answer for what's going to happen here is you're going to automatically send out to real. Okay, what is your username? You're going to receive this packet. You're going to automatically send it out. And for the purposes of these challenges, I think you got time. We wait a second between each message. You could just also rush to send this out also. So that's going to be your little secret there on that. That's what's going on there. If you get confused, probably you get a little bit confused. Why? It'll be like at first it'll be like, oh, this is so convenient that these packets are somehow automatically forwarding. That's why it's that IP forwarding thing. And then at some point you're going to be like, I really wish this would stop automatically forwarding. You can deal with it. Trust me, it's not too bad because it's like a 1 second delay between everything. And so that's what's going on here. Yeah, so I kind of actually meant to disable this IP forwarding this semester, but it slipped my mind. So here we are. So hopefully I'll remember after the semester to change that, because I think it would be cool for you to manually forward these things. And also maybe it's a little bit confusing that it's automatically forwarding these things. Okay. All right. Any more questions? I know we've talked about this a little more theoretically than I probably would have liked to. I guess one more quick demonstration here. Let's actually do one more thing. If we want to start sending out packets ourselves, we can do that. So we use this cool thing called Scapy. Go read the docs on Scapy if you want more information. But for example, I can create an Ethernet packet, and I can say source adder equals, hopefully I get this syntax right, IPA will do the correct thing. Do your actual source adder, because otherwise things could suddenly start getting dropped and it'll be confusing. Whenever you can do a real thing, do the real thing, because yeah. If you think about it, for example, if you declare, well, no, we're not going to go there. Just declare the correct source adder. Declare your source adder. And then destination adder equals 2, 3, 4, 5, 6. We'll just broadcast. So this, oh, I guess it's not source adder. Is it just source? Yep. Source, destination. There's docs for this. Okay. This has not sent anything out. So let's go back to TCP dump. This has not sent anything out. So I want to send this thing. and I want to send it over, oops, IPA. I want to send this over the ETH0 interface. Again, whenever you're sending a packet, you're sending it over some interface, over some port, over some physical Ethernet cable, right? It's going across something when we're talking about the Ethernet layer. And so that's what this interface thing means. We want to send it over ETH0. Okay, because I mean, I really don't want to send this over the loopback, because guess what? Loopback's definitely not going anywhere cool. And in our case, we've got two interfaces. We've got ETH0, we got loopback. Loopback's lame. Talk to ETH0. That's where this whole network, this virtual network actually is. So if I send this out, guess what? One packet just got sent. You'll see it says loopback invalid. I don't know what the heck that is. Probably we're just confusing TCP dump. If I say instead actually, let's even put an IP packet on top of this thing, an empty IP packet with nothing configured. Well, now we can see something's going on here. I don't know why it's saying localhost, but we can do, let's say, source equals 10.0.0.2, destination equals 10.0.0.3, right? And now we can see we've sent a packet from 0.0.2 to 10.0.0.3. I could send it to .100 if I wanted to, right? So now 2 is talking to 100. What does that mean? Again, there's just an interface. There's this ETH0 interface, and we shoot it out across that, and it's up to every device, whether virtual or physical in between, to do something with that. So the Ethernet layer is going to take care of the Ethernet layer. So we're saying send this to everyone you possibly can across this interface. So that thing is going to send it to everyone within this like physical switch, right? Within distance 0, distance 1, whatever you want to call it, of this guy. It's all going to go out. If someone's got their host configured where they're listening in for 10.0.0.100 because they think that's their IP address, because that is their IP address, or somehow they know that's their IP address, then stuff's going to keep happening from there. So, for example, if I do this and I put TCP on top of this, right, and I put source port equals 42123, desk port equals 80, and flags equals S for SYN. I think that's correct. Oops. And we build this. Oops. Is it just source again? Or no, I think it's S port. There's docs. Again, read the docs. So now we've just sent out a packet we've sent out a TCP packet here with this information. Guess what? I didn't get any response from 10.0.0.100. No one's configured to be 10.0.0.100. So you sent this out into the ether and no one cares, no one replies. If I instead send this off to 10.0.0.3, someone's going to reply. Look at this. Oh, nope, no one's going to reply. Something's upset. What are they upset about? Is there not a 10.0.0.3? I thought there was a 10.0.0.3. What the heck happened to 10.0.0.3? Oh, now at this point, okay, here's what we're going to do. Momentarily, we're going to give ourselves 10.0.0.2 back. It's saying network is unreachable because I don't have anything, there's no routes. We don't know how the heck to talk here. There's nowhere to go to. If I do IP adder add 10.0.0.2/16, I think is what we're normally on for this. Now I've got that IP address. Now I have a way to talk across this thing. And now if I netcat there and I arp-n, we'll see that happens. Okay, let's get rid of that. What happens now? Okay, still no one's talking. wondering if it's upset about this destination being FFFF. Let's take, since our kernel has already dealt with doing this ARP stuff, we'll just take it straight from the ARP table. Let's see here. We're figuring it out live. What the heck's going on here? Okay, look at that. Now it replies. So notice this. This is something I was unaware of. Unclear to me what's going on here. But if we use the correct destination MAC address, and again, you can figure that out by doing an ARP who has, that's what our kernel did for us for free. We just took that straight out of our ARP table. Once it did that for free, we can send the packet. Why does it not respond to FFFFFFFF? Honestly, not sure. It's possible that the kernel is configured such that the IP layer notices that the underlying layer below is a broadcast address. And it says, well, that's great that you're broadcasting this to everyone, but I refuse to do TCP over IP over Ethernet where that destination is a broadcast. I really don't know the answer to that on why. It's almost certainly an implementation decision somewhere along the chain. But notice how, right, when we broadcast out, no one wants to talk back. We send it to the correct destination, someone's ready to talk back. And just to test this also, ARP-N, if I do IP adder del 10.0.0.2 dev eth0, right now I don't have an IP address again here, and I send this out, I think it should still go. Yep, it still goes. And they are able, oops. They are able to respond back. I'd be curious here. Okay, so look at this. Now 2 is like, wait, that's us, 10.0.2. Why are we, who has, oh no, 3 is like, who the heck is 2? It's like panicking now. It like doesn't know who 2 is. And notice how it sent out 3 of these. Again, why did 3 send out 2? This is an implementation detail somewhere in the networking stack. 3 decided to ask 2 3 times in a row, where the heck is this guy? And we didn't reply. You don't see an is at because we deleted this IP address from our interface. So our kernel now is no longer going to reply because as far as our kernel is concerned, we're no longer 10.0.0.2. And so I'm curious what happens here. Yeah, look at this now. Now 3 is panicking. It doesn't know how to respond back. So before, when 3 had 2 in its ARP table, so it had it in its ARP table for a while, probably 30 seconds or a minute or something, and now we're not getting a reset packet back. Every time we do this, we're not going to get a reset packet back. Instead, 3 is just going to start panicking, saying, how the heck do I talk to 2? Like, I know I need to send a reset packet off to 2, but I don't know how to talk to 2. I mean, maybe it seems a little bit silly. It should be able to, maybe I'm not thinking about this right. It should be able to, if we wanted to, if the implementation decided to, pull the source MAC address off this guy. I'm not sure if that would be an issue to do that, but it in theory could. Probably there's an issue. There's definitely a reason why it decides to only respect ARP rather than just pulling it out of the Ethernet packet itself. But now it doesn't know how to talk to us. It's very sad. However, if I send it an Ethernet packet, so if I say, look at this, I send off to here, and actually I'm going to broadcast it. 1, 2, 3, 4, 5, 6. And I put ARP on top, and I do operation is at. And let me think about this real quick. There's docs that talk about this. I think it's p source equals 10.0.0.2. So the protocol source and hardware source equals this guy. And I don't even think I have to fill in the rest. We would play around with this if this doesn't work. So this is me. I'm talking to everyone. I'm saying is at P source 10002, hardware source this thing. So this is me like manually replying to this thing, right? Saying like, who the heck has 10002? And I'm saying, well, 10002 is at this hardware address. So if I send this, let's see what happens. Okay, so I sent, we can see that this went out. Now, what happens here if now I send a TCP packet again? Look at this. Okay, so it didn't like it, okay? We sent out a reply, 10002 is here. We can see we're still getting this issue. It's saying request who has 10002, tell 10003. That means whatever the heck we did with this ARP reply, it was not thrilled. So what I would do here is I was being lazy. I wasn't filling in the whole thing. Let's go ahead and fill in more. Let's say, I think it's protocol source, hardware source, protocol destination. Let's go ahead and tell 10003. Well, let's actually fill in only one. Well, trying to think here. I'm not sure what fields are strictly necessary for the implementation. In theory, this should be enough information, but it looks like it's not. Let's say protocol destination equals 10003, which means I am trying to tell 10003 that 10002 is at this address, but I'm telling it to everyone. At an Ethernet level, I'm telling it to everyone. At a ARP level, I've got a protocol destination of 10003. Let's see how it likes this. Not good enough. Hold on, let's check the slides. What do I say we do here? Okay, hold on. Let's do protocol or hardware destination equals 1, 2, 3, 4, 5, 6. Okay, 10002 is here, I swear. Huh. I wonder if it is a timing thing. Because I got a reset packet this time. Okay, we're like figuring out what the target likes here. So does this not actually matter? I do this. Okay, so let's say I do that, and it wants to know real quick, so let's quickly reply. So I say that, and then I get my reset. Look at that. And now if I do this again, I got a reset. If I do that again, I don't get a reset. Quickly send it out. I get a reset. I get a reset. Reset there. I don't get a reset there. It's like quickly invalidating. So it looks like for some reason it's not keeping this in the ARP cache for very long at all. It seems like it's keeping it in the ARP cache for like 2 seconds. I truly don't know why. So what if I do both? If I just like back to back. Unclear. Maybe we go the other way. So we know we're going to get asked as soon as I send this SYN packet. I know I'm immediately getting a request of who has. Yeah, look at that. So that ordering works nicely. Well, yeah, it works nicely enough. But you could imagine if whatever's going on here, you could have a script running just constantly sending this is at packet, and it looks like you'd be good to go. But something to consider, right? Like, and we're debugging this in a very different way, very different than the reverse engineering module and what this debugging looks like. We're just sitting here looking at TCP dump traffic and noticing that we keep getting this who has request. And we know how TCP works. We know that if I send a SYN packet, I better get a SYN ACK or a reset ACK back, probably. And if I get nothing back, it means that it doesn't know how to talk to me, right? So think about this while you're debugging stuff. All right, any final questions? Otherwise, I'm going to wrap up this office hours. Went a little late, but that's totally cool. But this is literally what it's going to look like to solve this stuff, right? Use TCP dump. Watch the traffic. You should be agreeing with things you're getting. If I'm constantly getting this who has stuff, if we don't send out this anymore, we don't get a reset packet. Not cool. We want our reset packet. Otherwise, this guy's not talking to us. It would have sent a SYN ACK instead if something was bound to port 80. But if we maybe just simultaneously do both, good to go. We get a SYN, we get a who has, we get our reply quickly sent out. These are all happening really fast. And then we get our reset. Cool. All right, yep, so this is what it's going to look like. Don't be afraid to use Scapy, read the docs. You might be setting up some while true loops and such. I guess one other thing I guess I will say is this is an interesting function. Sniff allows you to kind of implement, if you wanted to, a TCP-like behavior. So for example, if I do sniff, if I do def prn, args, quargs, prints, args, quargs, prn equals prn, iface equals eth0. What I have just instructed Scapy to do is kind of similar to TCP dump. So now if I go and netcat, well, I can't netcat because I don't have an adder. IP adder add. We'll just add ourselves an IP address back real quick. And then netcat 10003. That way the kernel can do lots of stuff for us because it knows what the heck's going on here. If I do this, we look at this, you can see that we got all of this stuff. We can see all these packets coming in. We can see an ARP packet happened, an ARP packet happened. Specifically, we've got this is, we got a who has, we got an is at, we've got IP with TCP sitting on top. So a TCP flags equals S. So a SYN packet went out, and then a reset acknowledgement packet came in, and then we got some ARP who has, blah, 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 blah. You're going to find that this setup here, it's in the docs. Read the Scapy docs. This is also going to be very useful for you. Cool. All right. Thank you, everyone, for attending my office hours. Hopefully you're enjoying your spring break. Hopefully you're enjoying the assignment. Good luck. I will see you next time. Goodbye.